Welcome to this explainer. We're going to completely demystify exactly how electric vehicles efficiently control their induction motors using open and closed-loop scalar control. I am absolutely thrilled to walk you through the engineering and the math that makes modern driving possible.
Okay, let's quickly hit our agenda for today. We'll be covering 1. The electric vehicle revolution, 2. The physics of driving, 3. What is scalar control, 4. Open loop control, 5. Closed loop control, and we'll wrap up with 6. The simulation results. All right, let's kick things right off with Section 1, the electric vehicle revolution background. To really set the stage here, we first need to understand the massive global push away from fossil fuels and why the three-phase induction motor has become this rugged hero in polling applications. It's fascinating how elegantly the propulsion system maps out. You have power moving from the main supplier and controller, straight through the converter, down to the motor, into the mechanical gear, and finally, right out to the wheels. The induction motor's performance just completely outclasses internal combustion engines, especially when we're talking about power density, transformation efficiency, and its honestly incredible low-speed torque characteristics. Moving right along to Section 2, the physics of driving, overcoming forces. So before we can even begin to control a motor, we really have to understand what it's fighting against, right? And that brings us to the dynamic modeling of an electric vehicle in motion. This perfectly illustrates the macro physics of driving. Because, your EV isn't just gliding forward in a vacuum. It is constantly battling a combination of natural forces that absolutely dictate the required mechanical torque. Every single dynamic shift represents a strict mathematical force that the motor just has to overcome. Let's break those down really quickly. First, the motor has to overcome rolling resistance, which is basically just the friction of the tires against the track. Second, aerodynamic drag. That's the literal wall of air pressure hitting the front of the vehicle as you speed up. Third is gradient resistance, which kicks in based on the slope or elevating angle of the road. And finally, acceleration force, which is the sheer physical force defined by Newton's second law required to get that heavy vehicle mass moving. The absolutely crucial point here is that by calculating and then summing these specific forces, we can figure out the exact engine torque the induction motor needs to output to keep you cruising at your desired speed. We calculate the individual forces, sum them all up, factor in the vehicle's velocity and the transmission efficiency to get our total power, and from that, we derive the exact engine torque. That resulting torque, that's the load our motor control system has to manage. Which leads us perfectly into Section 3, Scalar Control V/F ratio explained. So now that we know the harsh physical demands of the road, how do we actually command the induction motor to meet those demands? Well, the answer is scalar control. This is a highly reliable technique that simply adjusts the frequency of the power supply while keeping the voltage to frequency ratio perfectly balanced. By keeping that ratio locked in and constant, the air gap flux inside the induction motor is also kept constant. And that right there is the secret sauce to completely stable motor operation. It's all about that linear region where the constant V/F relationship ensures the motor operates smoothly. As the frequency increases, the voltage increases right along with it proportionally. But notice what happens in the field weakening region, at the higher end. The voltage just completely flattens out. That is a vital safety threshold. Voltage simply cannot overstep the motor's rated capacity, because if it does, we risk entirely breaking down the motor's internal insulation, and nobody wants that. Let's look at how we actually implement this in Section 4. Open loop control, keep it simple. Depending on the accuracy you need, scalar control can be executed in two main ways. We'll start with the simpler open loop system. Honestly, think of open loop like driving a car with a literal brick resting on the gas pedal. It's super low cost, extremely simple to implement, and completely immune to feedback signal errors because, well, there is no feedback. But unlike closed loop control, which utilizes PI controllers to constantly self-correct, open loop has incredibly low accuracy. If you suddenly hit a steep hill, it absolutely cannot adjust. Tracing the sequence of an open loop system, it goes like this. The user specifies a reference speed, the math computes the operating frequency and voltage based on that V/F ratio we just talked about, a modulation index gets calculated, and the inverter generates the power. But here is the kicker. There's absolutely no system in place to check if the motor actually reached the target speed. It just sends the power out and hopes for the best. And that glaring lack of verification brings us to Section 5, Closed Loop Control, Total Precision. Yeah, that hope for the best approach is exactly why high-accuracy applications like modern passenger EVs demand closed-loop control.
The critical component here is that decision point checking if the error is less than the allowed tolerance. The system is continuously checking the actual output speed against what the user requested. If the error drifts outside that tolerance, it routes right through a controller to course correct immediately. This is the feedback mechanism in action. It's very much like your car's dynamic cruise control. The actual speed feeds back into the system and is compared directly to the reference speed. The difference between the two is routed right into a controller, like a PI or a fuzzy speed controller. This controller calculates the exact speed difference and instantly modifies the signal heading back to the inverter. It guarantees the motor gets precisely the voltage it needs to maintain speed, regardless of any external forces throwing it off. Let's actually see the math in action in Section 6, Simulation Results Proving the Math. So, we've covered the physics and the control theories, but to prove which system is superior under real driving conditions, we turn to MATLAB and Simulink data. The researchers tested these systems against a highly specific, very rigorous driving strategy. What's really cool is that right at the 4-second mark in their simulation, they introduced a steep 20-degree elevating angle mid-drive. They did this specifically to stress test how the control loops handle a sudden massive spike in gradient resistance. And the crucial takeaway from the resulting data? Well, while open loop works totally fine for fixed-speed industrial tasks, the closed-loop system is mathematically proven to be significantly more precise for the dynamic, unpredictable environment of an electric vehicle. By using PID controllers, the closed-loop system dramatically reduces steady-state error, mitigates error sensibility, and delivers a highly smooth, high-performance speed response, even when the vehicle suddenly slams into that 20-degree incline. Which leaves us with a really fascinating final thought to explore next time. As cars start driving themselves and demand just unprecedented levels of microscopic precision, will the rugged, cost-effective simplicity of scalar closed-loop control survive? Or will even more complex methods, like vector controls, take the wheel entirely? Thank you so much for exploring this fascinating engineering with me today, and keep your curiosity in drive.